we want to talk about how fast things are going. The most common things is like basically how fast you're driving in a car and they tell you I'm going 100 miles per hour and you know, well, that's really fast because in 1 hour you travel 100 miles. Okay, so it's usually we take distance over time. Okay, so we talk about how fast things are going. We always say, well, if you're traveling fast, you take the amount of distance divided by the amount of time. So notice we have the delta sign here. Delta means final minus initial, so it's basically the difference from the beginning to the end. What difference have you like how far have you traveled? How much time has gone by? And you put those together. Now, you can't really do this for a chemical. You can't say, well, my beaker traveled 5 miles per hour. You don't say that, right? Because your beaker doesn't actually travel in distance. What happens in your beaker is yes, the reaction is happening, but how can you tell what's happening? So a lot of times you start measuring concentrations of your products and reactants. Yeah, if there is a question on the enthalpy of hydration, you can look up on our notes over there, but it's on slide number 17, actually 16 and 17, okay? And you can always ask me if you're not sure how to do it. I'll help you guys with that. So make sure you guys remember, so for the rates here, if you have a chemical reaction, you will do concentration over time. Okay, so it's going to be a change of concentration over change of time. And it's very important to know that over time, when you do a reaction, your products are increasing and your reactants are decreasing. Agree? So, let me show you in picture here. So if you look, A plus B goes to C over here. In the beginning, there's a lot of blue and red. And then at 16 seconds, there's less blue and less red. Why? Because those are your reactants. They're disappearing, so you can make C, some of the purple stuff. Okay, so you do know that over time, the reactants go down and the products increase. Now, because of that, the rate for this reaction is one number. If you were to calculate it and you only measured the reactant, you need to know that the change of reactant here is going to be a negative value. So because it's a negative value, we're going to stick a negative in front of it to counter that because we know it's going to slow down. We know it's going to go down in value. So we don't want a negative rate to represent here. We put a negative in front of the reactants, and then you'll get an answer here. So it says here, delta A over delta T. So let's look at A, okay? At basically at time 0, how many A's do you have? You have 8, 1, 2, 3, 4, 5, 6, 7, 8. So 8 was the initial. So delta is final minus initial. So that's final, that's initial. Initial is 8. What's my final? 1, 2, 3, 4. So it's 4 minus 8. So I knew that this was going to be a negative value here. And that's why for all the reactants, when you write the rate, you must put a negative in front of it. Okay, so negative of negative value here will make it a positive term. And then the time will be final time minus initial time. So you get 16 minus 0. And that equals 2.25 here if you use reactant A to measure your rate of reaction. Now, sometimes you can use B, just depending on which one's convenient. You don't have to do it for every single reactant and product. You can pick one of them, and then you should be able to calculate the rate. So in our lab experiment, we're actually measuring just one of our reactants is iodine. We measure the change of color in iodine and based on that time, and we wait till the iodine disappears to 0. So the reactant will go from something molarity to 0 molarity, and then you time that. That's what you'll be doing. So it will be essentially something like this, but our time is what you look at. But the final minus initial is your molarity at the end is 0 over there. Okay, so in this case here, let's look at C, our product. Initially, there's nothing. So initially, so final minus initial is 0 here. And then final here, you have 1, 2, 3, 4, so you put 4. Now, because it's a product, we don't need a negative sign in front of it. So 4 minus 0 over 16 minus 0, you get 0.25. So basically they're showing you, you can use any reactant or any product to calculate the rate of the reaction. Okay, as long as you remember the reaction better have a negative sign. The reactant has a negative sign in front of it. When they show you another example here, this is just a slower reaction, but they use X, which is a reactant, and then they use Z, which is a product, and they end up with the same value for that reaction. Okay, so I wanted to draw out a reaction here. So it's going to be H2 gas, okay, and then plus I2 gas. So leave some space because I want to draw the molecules out here. I guess you don't really have to draw it, but I like visually to look at it. Okay, and then it will make 2HI. So in this case here, you know how earlier that it was A plus B equals to C, and then X plus Y equals to Z is 1 mole, 1 mole, 1 mole, 1, 1, 1, right? This time here is not 1, 1, 1, it's 1, 1 to 2, the mole ratio there. Okay, so that's going to change a little bit some more. So hydrogen is a small gas, so maybe this is my hydrogen. Iodine is bigger, so I'll draw bigger ones. And then HI would be big one and a little one mixed together. Okay, so every time you use one H2 and one I2, you pop up with 2HI. Okay, now over time, if you're doing this reaction, H2 and I2 will go down in concentration. HI will go up in concentration. So if I wanted to write the rate formula, the reaction rate, so reaction rate for this chemical equation, so this is the overall reaction rate. So basically this experiment here at a given time frame, maybe you looked at it in like 10 minutes, 10 seconds. Usually we do it in seconds. So we have reaction rate. So if you wanted to write a reaction rate based on H2, okay, it would be, do you need a negative sign? It's a reactant, right? So you need a negative sign, okay? And then we have to take a look at the coefficient. This is, they don't write 1, but this is a 1 next to it, right? Agree? And that's a 2, okay? So what you want to do is, because this one pops up at 2, we have to make sure they all are on the same playing field here. So we divide by the coefficient. So 1 over the coefficient for this guy will be 1, okay? So that number goes down, okay? And then we will do that term, which is delta concentration of H2. So instead of writing all the words, when I use these brackets here, they will symbolize molarity or concentration now, okay? And then delta T. Delta is changed. Now remember, delta is final minus initial. Okay? So that's how you would represent that rate here in a formula term, because we don't have numbers. In the next question, we'll put numbers in. Okay? Now, can you write the reaction rate? Instead of writing with H2, could we use I2 to write it? Maybe we're measuring I2, which in our lab, we will be measuring I2, okay? So it will be a negative sign. And then 1 over, what's the coefficient? 1. And then multiply with delta, concentration of I2, over delta T. Okay? These two numbers will give you the same exact answer. I mean, these two formulas here. They'll give you the same answer for reaction rate if you put numbers in, okay? Now, we can also write a reaction rate by using HI, okay? So HI here is a product, so we don't need the negative sign anymore. We're gonna leave it as a positive. So product is a positive sign, reactants will be a negative sign because we know reactants go down over time, products increase over time. So it will be 1 over, what's the coefficient here? It will be 2, okay? And then you put your bracket and then delta, concentration of HI over delta T. So the reaction rate has a few pieces of information in it. You gotta make sure if you know it's a reactant, you put a negative sign. If it's a product, you put a positive sign. And also the coefficients of your equation here go down and you divide by the coefficient, okay? And then you multiply with this little term in here, which is a change of H2 or change of T, change of I2 or change of T, HI over time. So in this case here, we know that's the coefficient, right? So I'll write it down. Coefficient for H2. This one is the coefficient for I2. This one is the coefficient for HI. Okay? Now, notice there's another term in there in that bracket here. What does that term symbolize? Okay, so what does that term symbolize? This term here tells you this is a change in concentration of H2 over the change in time. So it's the, basically we know hydrogen gas, in this case is going to go down. It's going down, so it's disappearing. Okay, so we can say rate of disappearance of H2. Or we can just say change in concentration. I mean, but I know it's going to go down, so I'm just going to go ahead and say disappearance. Okay, so it means how much H2 is going away in a given time frame. And that tells you the rate of disappearance of just that gas alone. Okay, now what about this term here? This term now means rate of disappearance of I2. Okay, and this term over here is not disappearing, is it? It's appearing. So we can say rate of appearance. Sometimes people say formation appearance. I guess not formation too. Okay, formation of HI. So basically there's a lot of pieces of information for you to calculate reaction rate. The overall rate, you have to notice if it's a positive or negative sign, take into account the coefficient and the rate of appearance or disappearance of the item that you're speaking about. Okay, so that gives you the overall reaction rate. Now, so let's try to apply this in a problem, okay?
Professor, why is the top part of that fraction always 1?
Because I'm dividing by the coefficient, so I want to put the number on the bottom, divide, because I'm trying to make sure I don't, because if I don't divide by the coefficient, this will always be double the amount of these guys when I calculate it, whatever the coefficient is. So I divide it by the coefficient to make sure everybody is on the same plane. Okay, so you take 1 over. If you want to divide something, it's really this number divide by 1, this number divide by 2, but because I chose to write it on the outside, I have to put a 1 on the top here. It's just mathematical representation. The whole idea is to take this term, divide by the coefficient.
Okay, thank you.
Yeah, I just pulled it out to the side so you can see, so I write a 1 on the top here. All right, so let's go ahead and try in a question here. So here's my equation. So this is H2O2 plus 3I negative plus 2H plus goes to I3 negative aqueous plus 2H2O. Okay, and it says in the first 10 seconds, the concentration of I minus dropped from 1.000 molarity to 0.868 molarity. And they say, number 1, calculate the average or overall rate of reaction in this time interval. The reason why they say in this time interval is because over time it does, in the later time intervals, it does slow down even more. So they're just saying, let's look at this first 10 seconds and you tell me what's going on, okay? It will change for the next 10 seconds. So that's a one part question. And then on part B, I'm gonna write on the bottom here. Predict the rate of change in the concentration of H plus during this time interval. All right. So I'll let you guys write this for a few seconds here. I want to do a poll here real quick. The poll question is about your pet. If you have a pet, it says, do you have a pet? You have a doggy, a kitty, reptile, bird. I have a farm if you have more than one. And then you feel free to explain in chat how many animals you actually have. I know most of you have multiple. I should have let you guys pick up multiple options here. But nobody has a reptile, huh? Oh, actually, don't some people like keep like spiders too? I think, yes, insects. I had a student that really, really loved insects too. You don't have a pet, but you want one. Oh yeah, that was another option I forgot. Sorry. Yeah, if you don't have a pet, you can put in a chat, I guess, because I forgot to write. I have no pets. All right. So everyone get a crazy cat lady. You own one cat, straight. Aw. 2 snakes and 3 lizards. Plenty of reptiles. You have to click on the reptile then. I guess it kind of counts as a farm though, huh? 3 cats, 2 dogs. You guys are busy. Oh my gosh, you guys have the best pets. That's awesome. All right, so many pets. I know pets are good. 2 ferrets, 1 dog, and 1 fish. Husky, Morkie, and golden doodles. 3 lovebirds. Oh, that's so cute. 1 beagle. 2 dogs, 3 ferrets, and 7 rabbits. I used to have rabbits too. I had dogs and rabbits. The rabbits are so cute. All right, anyway, I think we had enough of a pet discussion here. So hopefully everyone here managed to see our poll here. Basically tell me about your pet, how many pets you have. We're gonna go ahead and end the polling. Basically most of us have doggies. Share results for a second here. And then we can close this and go back to our problem. So if you guys have ideas of other polls you want to have, we can do it. Like, I guess like sometimes like we see some gross ones like, do you like to eat McDonald's or Taco Bell? Like, what's your fast food preference? That would be a funny one. I think next one we should do that. Like, what's your guilty pleasure fast food or what you eat? All right, so let's go back over here. Calculate the average rate of reaction in this time interval. So remember when we said we want to calculate a rate of reaction, you can use any one of your items. You can use your reactants or you can use a product. So we're going to use what's given to us. So what did they provide with us? The information they gave us is on I negative. And I negative happens to be a reactant here with a coefficient of 3. Okay, so we gotta take that into account. Now, did they say how much it was changing? They said in the first 10 seconds, that means time 0 to time 10 seconds. The change went from 1 molarity to 0.868 molarity. Okay, so it is coming down because it's a reactant. Okay, so if I had to write a formula for I negative, based on this guy here, so we would say reaction rate equals to, do we put a negative sign or a positive sign for this guy? We're gonna do negative, very good. And then it's 1 over what's the coefficient? 3. Okay, and then we'll have to do in bracket, the little bracket term, which is rate of disappearance of I negative, which is the change in concentration of I negative over the change in time. Now let's go ahead and plug in these values in there. So I'm going to rewrite on the side, so negative 1/3. What's my change in concentration? So what's my final concentration? It's that one. It's final minus initial, okay? So 0.868 minus 1.000. And then what's my time difference? My final time is 10 seconds. My initial time is 0 seconds because you start in the first 10 seconds, you start at 0, you go to 10, okay? So it'll be 10 seconds minus 0 seconds. So the answer on the back side will be 10 at the bottom. You had a question?
Yeah, will time always be in seconds?
No, not really. But in our lab, we will be doing it in seconds. It's more common to be in seconds, but it can be different times. Later on in this chapter, you'll see we'll be doing like carbon dating. It's like thousands of years in time frame. Sometimes they mix the time units up on purpose to confuse you. Like they'll do in minutes and then in seconds, and then you have to make sure you keep your units straight. So yes, seconds is common, but occasionally they do come up with different units. You just have to be really careful to be consistent with your units. So what I like to do is always write them out so I don't get confused. Okay?
Thank you.
All right. So let's continue here. So molarity is up here in seconds. So our rate unit is going to be molarity per second. Okay, so depending on what concentration they gave it to you, if they give us molarity, we'll put molarity. So what's the answer here? So try to put this in your calculator and see what you get. So this was a negative number, but then you have a negative in front, it becomes positive. You have to divide by 3, and then you have to divide by 10 seconds here. So hopefully everyone gets about 4.4 times 10 to the minus 3 and units of molarity per seconds. So that's the overall, the rate, the big picture rate, right? That's the answer for that. Now, all right. So the next part here, they said predict the rate of change in the concentration of H plus. So they're not saying the rate of reaction anymore. They're saying change in the concentration of H plus. Now that's these little terms here. Changing the rate of change in the concentration. So they don't. They're to the point where they don't even tell you if it's going up or down. They don't tell you appearance or disappearance. They just say change. You notice that? But we can figure it out. Let's look at H plus. Is it a product or a reactant? H plus is right here. It's a reactant, correct? So it's really rate of the change will be a negative change because we know it's a disappearance. Okay? So when you calculate your answer, the rate of change here is going to end up being a negative number because we know it's coming down in value over time. So how are we going to use this to our advantage, and how can we predict the rate of change? So we got to go back to the key rate. Basically, the reaction rate over here can be calculated by using any one of these guys, correct? And if you just chose I negative, you use this formula. Well, we can write one for this guy as well, because we know that that guy will have the same answer over here. It's also going to be 4.4 10 to the minus 3. So then we can solve for the little piece that's missing. Okay, so I'm going to go ahead and write that again. So basically, the reaction rate, which we just solved for, is that one, right? Can also be written as using terms for H plus. So because H plus is a reactant, I'm going to put a negative sign in front of it, and it's 1 over the coefficient, which is 2. Okay, everyone's still following? And then what do we do? The next thing here is it's this term here, delta concentration of H plus over delta T. The good news is this is what they're asking for. That term is this in formula. So there's no need to split them up. That's one number as an answer right there. Okay, so well, that makes our life pretty easy then, because we know the reaction rate, right? What was the reaction rate? It was this one. So 4.40 times 10 to the minus 3 molarity per second equals to negative 1/2. My answer. I guess I'll write a big term. So we want to solve for this guy. Okay, that equals to basically that times that. Agreed? Well, times negative 2. Okay, so I will get negative 8.8. So you notice you can use anything in there. So if you wanted to really, we could write the rate using this, this, or this, as long as we know what sign to put in front of it and what coefficient to divide it by. Okay, so you can use any one in there, but the question always kind of directs you towards one or the other. You use always the most convenient one available. Any questions so far? Are we all still okay with this?
Is the answer negative 8.80 or 6?
It's 8.80 because it's 4.40 times 2.
Okay, I see. Thank you.
You're welcome. So let's try a couple more questions. Yeah, let's do a couple more. And then I'll show you some more slides. Let's go to the next question. Okay. C2H4Br plus 3Ki. So hopefully you guys are following this pretty easily. I mean, this is pretty simple material as long as you can keep your stuff, like, you know, the overall reaction rate separate from the rate of appearance or disappearance. This is 2 kBr, okay? I forgot to mark my K, so I'm going to squeeze my K in there. It's 2 kBr plus K. You will see stuff like this on your homework and quiz too. The rate of reaction is 2.0 times 10 to the minus 5 molarity per second. Find the rate of disappearance of Ki. That's one question here. Then we'll do another one after this. So they told you the rate. They asked you to find the rate of disappearance. So we can put it in the equation. Basically, we'll put the rate and we'll write the rate formula using Ki, which is one of the reactants. Okay, so my equation will be rate of reaction. So reaction rate is equals to, we're going to use this guy because the question answer Ki. Okay, so what sign is it in front of this guy? It's a reactant, so it's going to be a negative sign. Okay, and then 1/3. And then delta Ki over delta T. Okay, that would be the formula you would write out. And then since they already gave us a rate, well, that makes our life a lot easier. Let's put the rate in. 2.0 times 10 to the minus 5 molarity per second equals to negative 1/3, the term I'm looking for. So this is the rate of disappearance of Ki, right? So because you know it's a disappearance, you know your answer is going to be in a negative term. Okay, because it's simple. The negative symbolizes disappearance. Appearance is a positive value. So all you do is you literally take 2 times -3. Well, 2 times 10 to minus 5 times -3, right? So you end up getting your answer for delta Ki over delta T. That's going to be -6.0 10 to the minus 5. Not too bad, right? So if you see a question like this, you should be like, yeah, this is an easy one. It's an easy 5 points on earn on a test. And you will see stuff like this. Okay, the questions are not going to be all long, all super hard. It's going to be a mix. There will be some easy ones and some a little more challenging ones. But, you know, some students find this challenging because they can't keep their rate of disappearance separate from the rate of reaction. And they don't know about the coefficient and which term. So, I mean, it can get hard, but if you're following the material and make sure you're practicing and don't forget, it actually is pretty easy. Okay, so let's try another question. Here's another variety of that question. So you have another equation, 2NO plus Cl2 equals to make 2NoCl. Okay, and then the question is if the rate of Cl2 disappearance is 4.84 times 10 to the minus 2 molarity per second, what is the rate of formation of NoCl? So earlier they were like, here's the overall rate and find the rate of disappearance. Now they don't give you the overall rate. They just give you, here's the rate of disappearance for one of these guys and what's the rate of formation of the other guy. Well, you can still do the same thing. You will just have to write the rate for using Cl2 and the rate for NoCl and put them side by side because they're going to equal to the same number. Okay, so we can write the rate of reaction. So I'll write the reaction rate. If you have to use Cl2, it's a negative term, 1/1, agree? Because coefficient is 1. And then we'll do the delta Cl2, delta T. So this one here is rate of disappearance, which is that number right there. See how they gave you that answer? That goes right there, okay? And then that equals to NoCl will be positive 1/2. And then we'll look for delta NoCl over delta T. So they're saying this is 4.84. Can you find that term? Okay, so I'm going to go rewrite it up down here. So the reaction rate equals to negative 1/1 times 4.84 times 10 to the minus 2 molarity per second. And that equals to positive 1/2. Term I'm looking for, rate of appearance of NaCl. So we know that term equals to a negative 4.84. 10 minus 2. And then that equals to plus half and the term I'm looking for. So then we can solve for that term, okay? Which is basically this times 2. So we get 9.68. Did I miss something here? Yeah, this is positive because this is, oh yeah, I forgot this sign here, sorry. The rate of disappearance is negative, so this is positive here, right? Because it says it's disappearance, but they didn't put the sign here. I had to plug the sign back in here. So make sure you guys change that. Negative and negative becomes positive because the rate is never a negative number. And then that equals 9.68, 10 to the minus 2 molarity per second. And that is the rate of formation of NoCl. Okay? All right. So I want to show you guys some other stuff here. Everyone done with the math portion? Let me know if you still need a few seconds. All right, so let's go ahead and take a look at the slides real quick. So that was the same equation, right? And then I actually drew this out for you guys. Obviously, they have a better drawing. You can use the rate of H2, and that's what symbolizes like you have to put the term final minus initial. Same thing, we did this in math already, okay? So if you collected data over every 10 seconds, you notice that the rate does change in every, that's why they always say in the question, say in this time interval, just in this time frame here, because we know in a different time frame it will change. If you collect every 10 seconds, you get to see the change here. Sometimes the really fancy equipment, they can collect in time in real time, like in situ. So you can actually get a really like, not just in 10-second intervals, you maybe like milliseconds or femtoseconds intervals. But we're not going to do that in our lab, just showing you that it's possible. So when you see a picture of the rate here, we're not going to actually be doing the derivatives or anything like that here, but if you wanted to, you took a look at this equation here and they collected all these data points here. And they were saying basically, if you used a reactant versus using a product, you should actually still get the same rate in the same given time frame. So they're looking at 50 seconds here. And no matter, so if they pick 50 seconds, they pick the numbers here and then they got their numbers, the rate is the same. So in any given time frame, like maybe the rate for 80 seconds for H2 will be here. You calculate from this point here, and then HI you calculate from this point, you will end up getting the same answer. Okay, so that's something useful that we can take advantage of. And then here's what we've been doing, the formula. You can write the formula for every single reactant or product. Just remember what sign in the front and what the coefficient is that you divide with. Okay, so that is the rate of reaction. So that's one portion of your lab that you will have to learn how, that's for rates of reaction lab, which is after this week's KF lab. So you have a little bit more time, but since I still have a little bit more time, I want to talk about how the lab class sort of measures the rate. So a few ways to measure the rates. What we're going to actually use in that is looking at colors. So when you have colors, you can actually put it through a spectrometer, UV, you guys remember, well, if you've done all online, you might have not seen it, but you can stick your little sample into a machine and it will tell you, like, depending on how dark the color is and what color it is, it will tell you the concentration in a number called absorbance. A lot of times they use the absorbance value to calculate concentration, and then you can get rates from there. Another way is to inject it into a chromatography and a gas. So they shoot it in there and then they collect. They actually can measure how much of each portion you have. So you have to collect samples at different times to do that. So what we're actually doing in the lab is really playing to the advantage that you can see iodine's color. Iodine starts off as like brown in the solution. And then over time, as the reaction goes, it actually clears up. So what you're going to be doing is the time that's recorded is basically from the beginning time 0 until the color disappears. So there's an initial molarity and the final molarity will be a 0. So a lot of times you do the rate calculation by just taking the molarity of iodine divided by the time. And people don't understand, why am I doing that? It's because in lab, you're physically observing the change in color of your iodine. Okay, so that's what you will be doing. So, and based on that data, a giant table here, you will actually be building a rate law of your experiment. So what in the world is the rate law? So it's really a mathematical relationship that tells you the relationship of the rate of the reaction compared with the concentrations of your reactants. And every reactant behaves, it can affect the rates differently. So we have different kinds of orders. And the rate law here must be determined experimentally. That's why we do a set of experiments. You'll see in your data tables here, okay? So there's a few things here to look out for. So here's the rate of the reaction, overall rate, okay? And here's a little k here. Now be really, really careful to not write capital K. It's a lowercase here. This k here is the kinetics k, it's a rate constant. It's about how fast things are going. The next chapter we have, all the k's are capital and it's the equilibrium constant. It's a different thing altogether. So I just want to make sure you guys have a good habit. Start writing as a little k, okay? So rate equals to rate constant times the concentration of A, right? Concentration of one of your reactants, because A is right there. And then B to the power of N, and then concentration of B to the power of M. And you're like, what is this power stuff here? So the power stuff here symbolizes the order of your reactant. So A is the order of N, B is the order of B is the order of M. And these orders here are whole numbers that we're going to focus on. It could be 0, 1, or 2, and each order means something different. Okay, so I wanted to show you guys, I guess we'll talk about that and I'll show you an example of how we can put it together. Okay, so in this next slide here, you'll see that 0 order means the rate is independent on the concentration of A. Your A could be 1,000 molarity or A could be 1 molarity. Doesn't matter, it won't change the rate. Okay, if it's 0 order, however much A you had, it doesn't really affect the rate. The rate will stay, maybe the rate was 10 molarity per second. You had 10 molarity here, that would be 10 molarity per second. If you had 100 molarity here, that would still be 10 molarity per second. The rate doesn't change. You know why it doesn't change? Because when n is 0, anything to the power of 0 stays at the same number as 1, so it doesn't change ever. Okay, so the order is to the power of something, and when you get to the power of 0 is 0 order. When the power of 1 is first order. So if you do to the power of 1, the rate then is directly proportional to the concentration of A. So if your A was doubled, your rate would double. If your A was tripled, the rate will triple. So that's first order because it's to the power of 1. Okay, and then there's a second order here. The rate is proportional to the square of the concentration because instead of to the power 0 or 1, it's to the power of 2. So everything is squared. If your changing concentration of A is double, your rate will change 2 squared, which is 4 times. Okay, so that's what we'll be looking at. And then they'll show you these graphs here. They're showing here the change in 0 order is not affected by the concentration. This is concentration here, so it's just going to go the way it wants to go. First order does affect it, second order affects it. And then here, rate versus reactant concentration. You see how the rate doesn't change even if your concentration changes for 0 order? That's because it's to the power of 0. And if it's power 1, it's directly proportional. So if it goes up, if your A goes up, your rate goes up. Now, if it's a second order, it starts to curve because it's a square concentration change. All right, so let's go ahead and put this in terms of like, how would you be able to observe this on a set of data? Okay, so I'm going to simplify a little bit here. We'll just say right now we only have one reactant, which in reality you always have multiple reactants. Okay, but let's just consider one reactant right now. So the rate here, if I have just one reactant, let's call it A, is equals to Ka to the power of N. Okay, so only one reactant, simple case here. Let's talk about what it would look like if it was 0 order. If it was 0 order, N would be 0. And when it's 0 order, we also remember reading that it says rate is independent of the concentration of A. Okay? So if you wrote it out, the rate, that's a number like maybe like 5 times 10 to the minus 3 molarity per second. That's the rate, something that we've been doing in the previous part. That equals to the rate constant times A's concentration to the power of 0. So you see, because it's to the power of 0, the concentration here won't affect the rate because it can't. Anything to the power of 0 turns to 1, so the rate is just equal to K at that point. Okay, so that's important. So if you had something that's 0 order, you did multiple reactions to see the rate changes. Would it change the rate? So I like to call it initial rate because the rates do change over time. We'll just in one given time frame here. So we'll do 4 sets of experiment. Okay, to my first test tube, I'm going to put in a 0.10 molarity, and I'll measure the rate. Maybe the rate comes out to be 0.015. Okay, and now if this was zero order, no matter what concentration you changed it to, what would the rate be? The same exact number. Okay, so let's say I decided for my second test tube, I'm going to go ahead and double up my A. I'm going to put, instead of 0.1, I'll put 0.2 molarity in. What do you think the rate will be if this was a zero order? It would stay as 0.015. Okay, it does not change the rate. So if you start seeing stuff like that on a table, where even though the concentration here changed, the rate doesn't change, that guy is a zero order. That's just like a signature for you to observe, okay? So what if I was like, oh, let's double check this again. I'm gonna double it again. Maybe I'll go to 0.4 this time. Do you think it's gonna change the rate if it's zero order? No, it's not gonna change. It's gonna go to 0.015 still. It won't change it. So you can do whatever number you want. Let's do another 1.5, and you'll see the rate is still 0.015, provided that this is the only reactant there. When you have multiple reactants available, you have to make sure the other guys aren't contributing to the change and only focus on one at a time. I'll show you examples of that later on. But this is just simplified case. If you saw a zero order reactant, this is how it would affect the rate. No effect. Okay? Now, let's go and do the first order real quick. Ka to the power n. So first order n is 1. So in this case here, rate is now directly proportional to the concentration change of A. Okay, so we have that. Now, if you were to see this on a table, it would not look like the zero order chart. It will look a little different because it's going to change. It's not going to stay stagnant in the rate the whole time. So let's do 3 right here. 1, 2, 3. Okay, so if I started off at 0.1 and I got my rate was 0.015, right? If I totally did a second test tube and I put 0.2 in there, I had basically if 0.1, A is 0.1, it gives this rate here. When A is double, you see how it went up 2 times here? From here to here is times 2, agreed? Now from here to here, the rate will be times 2 to the power 1 because it's first order n is 1. Okay, so then you'll be like, oh, well, basically I'm going to observe 0.030 as my answer here. Okay, so basically it's saying whatever your rate concentration changes, it's reflected in the rate change because it's the same exact number. 2 to the power 1 is equals to 2. That's why they say it's exactly directly proportional. Okay, now what if you did one that's a 0.5? Then you're like, well, it went from 1 to 0.5. You can do whichever lines you want to compare. I always pick the easiest ones to do the easy math. So from 0.1 to 0.5 is times 5 times. So what do you think the rate should change here? Times 5 to the power 1. Agree? So 5 to the power 1, so 0.015 times 5, you should get 0.075. That's how you would see the rate change for first order, okay? Now I want to show you real quick, since we're talking orders, the last one that I want you to learn is second order. So if this is second order here, your n here equals to 2. This is second order. Now in this case here, rate is now proportional to the square, okay? Square of concentration change of A. And if I ever wanted to see it in a chart, What will we observe? It would always go up like a lot more, okay? So let's say if I start with 0.10 here, and then I get 0.015 here, just to show you a comparison. And if we did 0.2 of my second test tube, this is going up by 2 times, right? How much would this go up by? 2 squared, which is 4 times. Okay, basically the order tells you how many times the power it to. So that would give me an answer 0.60 right there. And then if we were to do it to 3 times, so this is here times 3, right? This rate here would change times 3 squared, which is 9 times. So you get 0.135. You see how the change is a lot bigger now. It's going to be squared. So second order is squared, first order is to the power of 1, 0 order is to the power of 0. So we talked about 0 order, where 0 order, the rate is independent of the concentration. So no matter how you change up the concentration from one experiment to another, the rate is unaffected because this reactant here is 0 order. This reactant's concentration change does not affect the rate at all. Okay, it has to do because it's a to the power of 0. Anything to the power of 0 equals to 1. That means there's no change. Anything times 1 doesn't change, right? So that's why that's 0 order, okay? Now, first order, it says it's directly proportional to the concentration change. So that means it's anything to the power of 1. So when we write it, I'll add it here, rate equals to K, A to the power of 1. Anything to the power of 1 means K to the A to the power of 1 means K times A, right? So the concentration of A is going to be, if concentration of A is changing, the rate will change with the same amount because it's constant times the concentration of A. Okay, so if I find out the first experiment I did 0.1 molarity right here, and the K is a constant. My rate ends up being 0.015. If I doubled it to 2 times A, you know how 0.2 is 2 times 0.1? So that means there's 2A here. So rate now is equals to K2A. So it just doubled. So that's why the amount here doubled, because it's 2 to the power 1 equals 2. And then if you do 5 times here, and you can compare whichever 2 lines you want. You can say, well, from line 2 to line 3 is 2.5. So you just take this and multiply by 2.5. So just whatever works for you. I like to pick whole numbers so it's easier. So this is going by 5, and then this is going by 5. Okay. Now, second order is square. So A has to be squared, the concentration. So rate equals to K and then A to the power of 2. So it's squared. So the effect of this concentration change here is always going to be squared. So the rate is going to be a bigger change here. So for example, if you go from 0.1 to 0.2, it's 2 times, and then it's going to go from here to here is times 2 squared. So it mimics that number, but it takes a square there. So like that's a 2 here, and then that's a 2A, and then squared, okay? So and then if you go from 0.1 to 0.3, it's times 3 squared, it will go up 9 times. So that's just basically how you would see them on a table. So I want to go ahead and basically put it in a question now. So I'm going to do 4 experiments here. We'll do 0.1, 0.2, 0.2, 0.4. 0.1, 0.2, 0.1. Okay, so here are the molarities. Now in your lab, you're not even given the actual molarities. You have to calculate the molarities of each sample. Okay, so I just want to make sure you guys are aware you do have to still calculate that because they gave you stock solution concentrations that you have to mix together. And based on that, you have to calculate the molarity. So just remember, don't copy the molarity straight from the procedures. You have to recalculate it. But anyway, here's some molarities already given to you guys. So here's test tube 1. Test tube 1 is the first reaction they tried. They did 0.1 of NO2, 0.1 of CO, and then they got this rate. Okay, and then they did a bunch more. They did a second test tube with this, third one, and a fourth one. And then they just compiled all their data together. So that's how you will, usually you have a few trials, a few different reaction mixtures, and you will use this information here to try to predict the rate change, the rate law. Okay, so I wanted to show you basically what we've been talking about. Now, earlier, I was simply talking about one reactant, agree? Now I have two reactants. Well, what am I gonna do? I can't, if each reactant, both of them are changing, then I'm gonna have a hard time figuring out which reactant contributed to the rate change. Okay, so as if like, if you have two little toddlers in a room with a really expensive antique that's like fragile, like breakable. Maybe like a really expensive, I don't know, something made out of glass, like maybe a sculpture that's glass sculpture, yeah. And then there's two kids in there and they're playing. Now, if both kids were awake, you don't really know who was the one breaking it if the thing got broken. Because they could say, well, he broke it, or she broke it. You're not really sure. Now, unless one of them was not feeling well and they took a nap, they were sleeping, and only one kid was awake at that time. If one kid was awake at that time and the thing broke, it's because of the kid that was awake, okay? So in this case here, you wanna make sure if you have two reactants, make sure one of them is asleep and only one is awake and changing and moving, okay? Now, if you have three reactants, make sure two of them are sleeping and only one is awake. So basically, you have to always pick conditions where only one reactant is changing, the others must be asleep and not changing. And that's the only way you can track and say confidently, well, the rate change is due to this guy's change because the rest of them are constant and not changing, okay? So I want you guys to take a look at this table here and start coming up with some lines here, okay? To tell me which two lines can I use to compare where one of the reactant is constant and the other one it's changing. Any ideas? So there's gonna be quite a few combinations available usually, okay? So I like to pick what's convenient. So any ideas, anyone? Take a look and see where one of them is changing. You gotta pick two lines, only two lines, because you're only comparing two of them for, at each time, okay? Where, right, the others become control and they shouldn't change. So in this case here, since I only have two reactants, basically one is changing, the other isn't. Okay, if I have multiple reactants, more than two, you make sure all the others aren't changing except for one. Okay, so here's a suggestion. Someone said 1 and 2 for number 2. So 1 and 2, for NO2, not number 2. So if you look at 1 and 2, lines 1 and 2, take a look here. This guy is changing, that guy is constant. That means the rate change here is based on the change of NO2 by itself. So that's good. That's one example, okay? So I guess I'll go ahead and write it down. Compare lines 1 and 2. So I don't want to draw on it right now. I'm going to rewrite terms down here so I can kind of like work with that, okay? There's another suggestions. Let me see. Lines 2 and 3. Yeah, we can use 2 and 3 after this for, see how 2 and 3 is this guy is not changing, that one's changing. So the change of this is going to be affecting this rate here. That would be for the second reactant, CO. Okay, so just remember, this is one reactant, that's another reactant. So basically, if you had two reactants, you need to pick two scenarios where one is changing, the other isn't. So you can determine each reactant separately. Okay, so this one here, we're going to determine for NO2. So I'm going to rewrite it out so I can scribble all over. Usually you don't have to. Once you get familiar with it, you can just work straight from the table. It's just that it's the first time you're kind of doing it. I want to make sure you guys understand. Like instead of a bunch of lines all over your table, when you study, you're gonna be like, "What happened there? I don't remember." So this, I'm just gonna rewrite it out. Okay, so lines 1 and 2. Okay, so we said this one was going up by 2 times, right? So sometimes the numbers aren't pretty like this, 0.1 and 0.2. We always say, yo, duh, it's 2 times. I can see it clearly. But if you couldn't see it clearly, I like to take the big number, divide by the little number, and you get the answer here. And whatever the big number is, I do the same positioning. So I take bottom divided by the top, I get 2. So that one divided by top, I get 1. So there's no change. This is constant, right? So it's times 1, so I just write constant right there. It's sleeping, okay? Now, the rate change here, what was the rate change? So you do the same pattern. Bottom divided by the top. What do you get? You see that this is about times 4. Agree? It's not going to be perfect because you have experimental data. And experimental data isn't going to fit perfectly every time. So keep that in mind when you're doing stuff in your lab. But I also want to show you another method that the lab shows you is mathematical. This one is just like basically just looking at the graph and looking at the data and you can determine. Okay, so this is times 4. What does 4 equal to when we say is times? 4 is actually times what? 2 squared. Okay, because it's 2 squared, what order is it? It's second order. Okay, so and from here, I know that NO2 is second order. Okay, so that's how you will work to find the rate law. So in the first one, you say, okay, I know this guy's second order. Now, so that's how I would do it. Usually this is the, just basically look and see, determine the way. Now there's another method that you will use in the lab as well, because sometimes our numbers in lab are so crazy, it's hard to see evenly that it's exactly 4 and stuff. So I want to show you a mathematical way. But I would say in class, in lecture, stick to whatever way works best for you, whatever is faster for you. Okay, for me, this is a lot faster, so I can visually see it. But let me show you how you can also use a different method to determine that this is second order. So the thing is, you have to pick your 2 lines. So we picked lines 1 and 2 here. So yeah, so we have another suggestion that says line 1 and 4. Now line 1 and 4 is actually for NO2 as well, because this is going by 4 times, and that one is constant. So we can use either line 1 and 4 to do for NO2, or use line 1 and 2 like we did over here. So basically, you only get to you need to only do it once. But if you did lines 1 and 4, you'd see you get the same result somehow. Okay. I feel like I might have written it. Yeah, good. All right. So in this case here, for the second method, you'll probably see this in your lab. It tells you, once you pick your 2 lines, you write your 2 lines on one on the top and one on the bottom. So I like to write the big one on the top, like the second one. So I'll write rate 2 on the top. And what's the formula for rate 2? Well, I have two reactants here. Rate 2 equals to rate constant, right? Because that's what we said, it has to be equal to a rate constant times my first reactant, NO2, to the power of, I guess we'll call it N, because we don't know what order it is yet. And then we say the second, and also multiply with whatever other reactant I have in there to another different order. So in this case, CO to the power of M. So that's how I would write my second rate here. Now, and then I can divide this whole thing by writing rate 1 on the bottom. So rate 1 equals to K, again, a rate constant. Because it's the same experiment, it will have a rate constant here that's at the same temperature. When the temperature doesn't change, the rate constant stays the same here. So K here times NO2 to the power of N times CO to the power of M. Now the thing is, rate 2 and rate 1 have numbers in here. Concentrations of each reactant has numbers. So what you have to do is you have to plug it in. Okay? All right, so let's go ahead and plug in all the information. So I'm going to go ahead and fill in the blanks for rate 2. So rate 2 is that one. So all right, 0.0082, and that's molarity per second, but I'm not going to bother with the, well, I guess we can, but there's a unit and molarity per seconds right here. And then K is a constant. We don't know what it is. But we do know that between line 1 and 2, the temperature did not change. So the K will stay the same. So we'll just keep it as a constant right there. Now, what's the concentration for NO2 for line 2? It's 0.2, so I have to fill that in. And then that's to the power of N, and then I fill in the concentration for CO to the power of M. So this is what you will have to do to show your calculations in the lab, because the numbers may not be really pretty, and sometimes this helps. Especially like when you have like post-stat questions, or maybe on a final exam where the numbers aren't going to be perfect. But if you use this method, it will always work, okay? So in this case here, you take that, and then you write the first guy's rate, that's 0.0021. It goes to K, and then the molarity of the first one, 0.1 to the power of N, and that one, 0.1 to the power of M. Now the next thing is you start looking and see, well, there's a lot of things that I can cancel out. So this K and that K, K over K becomes 1, it cancels out. Okay, now, although I don't know what power of M is, this is 0.1 to the power of M, and this is 0.1 to the power of M. They cancel off because they'll divide each other out. So again, I can cancel that term off. So from rate 2 and rate 1, I can solve for N because now there's only one unknown. Okay, so how can I solve for this unknown? You take this divided by that, and you get 3.9 here, about 4. And then now you have 0.2 to the power of N to 0.1 to the power of N. So I guess I'll go ahead and write it out and show you. Right? Now when you have something like this, you can basically put the 0.2 and 0.1, clump it together and take it to the power of N. Agree? So now what's 0.2 divided by 0.1? So 3.9 equals to 0.2 divided by 0.1, which is 2 right here, and then to the power of N. So to solve for N, you just basically use the log method here. So you put the log of 3.9 equals to log of 2 to the power of N, and that equals to N log 2. And then N is the term on its own here, is log 3.9 over log 2. So you get 1.96, and since we're talking orders here, is 0, 1, 2, and sometimes there's half orders, but there's no 1.96 order, okay? So you will want to go ahead and round it to 2. Okay, so you will be rounding, okay? So you're rounding to whole numbers or halves. but we only focus on whole numbers in the lecture. But sometimes you will run into halves. It's occasionally you will see that. Okay, so there's two methods that we can do that. So we just figured out n as 2 from the log calculation method, or you can use what I showed you up here, where you just kind of take a look and you can kind of tell, well, if it's 4 and 2, I can kind of know it's 2 squared. Okay, so you didn't have to, I mean, it literally tells you the same thing as 4 and 2 is 2 squared. Right there, okay? So the same method, just showing you mathematically how you can write it out. Okay, so we also had another suggestion earlier. So that was for NO2, and then someone said you can do lines 1 and 4. Lines 1 and 4 would help you determine NO2. So I don't have to do that again. You could have chosen to do 1 and 4. The other reactant that we had, someone mentioned that we should try to do lines 2 and 3. So with lines 2 and 3, I'm going to go ahead and just write on here, okay? Are you guys done writing this stuff here? Okay, so I'm going to go ahead and move it up here. So lines 2 and 3, you have, this one here is constant. This one is times 2, agree? And what's this one? It's not really changing, okay? It's probably changing just a little bit due to experimental error. So I'm just gonna go ahead and say this is constant. So basically, if CO doubled, the rate is unaffected. What order is CO?
First order.
It's unaffected, okay? So take a look at this. Times 2 and constant. I'm gonna show you what first order looks like. When it times 2, it doubles. That's not first order, okay? So when you times 2, it stays the same. See that? So it's actually 0 order. So make sure you guys do practice, because you want to get used to looking at these numbers here. So now let's come back here over here. We said this is times 2 and that one's constant. That means this one here is 0 order. Okay, just whenever you guys have a little doubt, you're not quite sure, always take a look at the other thing that we started off with and see how it changes, and that kind of helps you remember, oh yeah, maybe this is 0, this is first, this is second. Okay, so now that I found out this reactant is 0 order and that reactant is second order, I can actually write out the rate law and show you. Okay, so I'm going to go ahead and write out the rate law. What we do here. So rate law is rate equals to K NO2 squared CO to the power of 0. Okay, a lot of times if it's to the power of 0, they don't even write it anymore. Sometimes they just kind of, because anything to the power of 0 is to 1, so you don't even have to really write it. Okay, but that's the rate. Now, sometimes they'll ask you to calculate K. Okay, now in your lab, you will be asked to calculate K. Now, what you guys will have to do is find the order of each of your reactant, which you have 3 of them. First, you have to calculate the molarity of all your reactants on your own. You don't even have that. You have to build a table yourself. You have to calculate the rates based on the time. So you have to build a table, figure out which 2 lines you want to use for each reactant. Find the orders for each one. So once you find the orders, they'll tell you, go ahead and now calculate K for every single line. You got to calculate K for this line, K for this line, K for this line, K for this line, basically. Yeah, I'm going to show you just the first one. What you want to do in lab is actually calculate the K for each reaction mixture, and then you take the average K and then put it here. And technically, the K should stay the same if it's the same temperature. But because there's experimental error here and there, it does vary a little bit, okay? So to find the K, let's say we just do it for the first line. You literally plug in all the values from the first line, okay? So the rate from the first line is 0.0021. I'll plug it in here. Okay, that's molarity per second, and then I'm looking for K. We don't know what that is. And then NO2 is 0.1 molarity squared. And then CO is 0.1 molarity, but that's to the power 0, so that term essentially just goes away. Anything to the power 0 equals to 1. So 0.0021 molarity per second equals to K, and then what's left over here, basically I'm just rewriting it. Okay, that's square, and then that term just disappears, it turns to 1. So now if I want to solve for K, I take 0.0021 molarity per second divided by this term 0.10 molarity squared. So when you square the molarity, remember this number squares, the unit also squares, okay? So what you end up getting here, this is 0.01 after you square it, and you take 0.0021 divided by 0.01, you get 0.21, and then the unit is molarity per second, and then here's another molarity squared on the bottom. So it's molarity to the minus 1, S to the minus 1. Okay? I guess I'll write it over here on the side to make sure you guys see it. So that's how you would get your answer. All right, so that would be the K for line 1. So if the question on the lecture asks you for K, you can just pick whichever line and your K should be the same for every line, so just pick the first one. Now in lab, because there's experimental error, you'll do the K for every single line. So we just did the one for the first line. You do the K for the first line, K for the second line, third line, fourth line, and then average all those Ks to get your average K. Okay, so that's what you'll have to do. Now, I think we should keep practicing. So now I want to show you another question. This time we want to do one with 3 reactants. I think. Let's go ahead and do that, okay? Everyone ready for that 3 reactant question? Okay. All right, so let's practice now. We want to do MnO4. H2C2O4. So you can do whichever method works for you. You can use your log method if you feel more comfortable with math. I like to do what's faster, so I just like to look at the table and be able to figure out what orders it is. But either way, you know both ways, okay? So I'm gonna go ahead and write out all the concentration. There's a lot here. So basically the question is find the rate law. Okay, and then we'll have to find the orders for each reactant. And then we want to also get the K. And in this case, I'm just gonna do the K for line 1. So I'll give you guys some time to kind of take a look at it. And then once you finish writing, I want you to give me suggestions on what lines we can use for each reactant, okay? right, while you guys are doing the writing and figure out your lines. So someone said lines 1 and 2, and then lines 2 and 3, and 3 and 4. Yeah, that works. Okay, that's a suggestion. Those work for me. So Dylan gave us some suggestions. I'm gonna go ahead and give you guys a poll while we're doing this. Oh yeah, this is a gross one. It's funny. What's your go-to fast food place? Multiple choice, and you can choose whatever. So here's the options. No thanks. It's actually you, no thanks. McDonald's, Taco Bell, Burger King, Chick-fil-A, PDQ, Popeyes, KFC, Wendy's. Some other chain not listed here, tell us in chat. All of them. So, what's your go-to? Why though? Is it because they're yummy or because they're convenient? Fresh Kitchen, okay. Chipotle, Jollibee. I've never heard of that one. Jollibee. I love Taco Bell, but it's got COVID. Really? Taco Bell is the easiest to turn vegetarian. That's a good point. Oh, one of us works at Chipotle. Cool. That's awesome. All right, so I tried Chick-fil-A a couple times during a trip. It was really delicious. I agree, it is delicious. I guess Jollibee is not really a fast food then if you have to wait. Well, I guess you still have to wait at McDonald's or Taco Bell, right? If it's busy. Culver's. I've never been to those places. I don't even remember the last time I went to get fast food. It's been over a year. I have had Fresh Kitchens and Chipotle, so I guess those count. Concrete mixers, yum. No time to cook. All right, so everyone wanted to vote, all got votes down. Someone said Chick-fil-A, so we had our options. I'm gonna go ahead and end the polls. Still got some people not answering. They refrain from answering here. Wait, what? He concrete. It's a name, I think. It's not actually concrete. It's like ice cream, isn't it? And you mix stuff in it. Okay, let me go ahead and share the results. So we have 5%, only 2 people said no thanks, and then a bunch of us said like all of it and all other options. So we have McDonald's, Taco Bell, Chick-fil-A won. Chick-fil-A was the clear winner there. At Culver's, it's ice cream. Yeah, it's pretty much ice cream. Class trip to Chick-fil-A. Well, it is really close to, like you can literally walk there if you're in Clearwater campus. It's so close. Anyway, I'm gonna stop sharing this result here. We have to go back to talking about numbers instead of food. Hope you're not hungry. Seminole campus is right down the street. That's awesome. I think they had a good idea trying to plant these places right by schools, huh? Everybody will go there and eat. There's pretzel buns at Culver's, south of Gibbs. Oh, you don't have to. Well, Gibbs has other places too, so I'm sure they have other options there. There's Taco Bell there, I think somewhere. Yeah. Anyway, let's go back to over here. Okay, so we had some suggestions. We said someone said lines 1 and 2. Do you agree? Let's take a look at lines 1 and 2. Okay. So I'm gonna write down lines 1 and 2, and you tell me what's line 1 and 2 gonna help you with. Okay. So MNO4. I guess we don't have to keep writing it out, but I'm gonna write it out for this question, and the next one I'm gonna start drawing lines on the tables. Okay. So you'll have at least like 2 of them where the tables isn't too messy. So 1 and 2, you have 1.0 10 to the minus 3. This is 2.0 10 to the minus 3. And that's 1.0, 1.0, and this is 2. and this is 8. So you guys see how these are constant, right? So I'll write it up with red. This one's constant. I'll just write C here because there's not a lot of space there. That's constant, right? What's the change here from here to here? That's times 2. Agree? What's the change from here to here?
Times 4.
Times 4. And what does times 4 equals to when you have to use 2 as a number? It's 2 to the power of 2. Agree? So what order is that guy? So MnO4 is second order. Okay, so we got that one. Then we can do lines 2 and 3. Now, remember, it doesn't have to go in order. You can go whatever order you want. It just so happened that the orders that we have here are conveniently kind of sort of in order. You can do 4 and 1, 3 and 1, 3 and 2, it doesn't matter, okay? But we're gonna do lines 2 and 3 for the next reactant. So let's see what lines 2 and 3 give us. I'm gonna go ahead and write it out. So whatever you do, the lines you pick, you want to make sure you pick only the lines where one reactant is changing and the others are constant. If you do accidentally pick one where the lines, a lot of them are changing, it's gonna be really hard to determine which one caused a change in the rate. So in this case here, what do you guys think? That one's constant. That one's constant, right? So someone says first order, let's double check. So this is times what? Times 2, agree? What is this one, times what? So a lot of people are like, what's 8 going to 1.6? And they're like, actually it's 8 going to 16 because you see how this is 10 to the minus 4 and it's 10 to the minus 3. So that's actually times 2 here. Okay, so make sure to not only look at just the front number, make sure to look at what's behind it as well. All right, so that's times 2. So times 2, that equals to times 2 to the power of 1. So yes, it is right. H2 C2O4 is now determined as first order. Okay, so we can do this. Now, remember, the other way is to take this whole line's rate law divided by this whole line's rate law and then solve for it using mathematical. And some of you are really, really fast at doing that, so you can do that completely okay. For your lab, I do want you guys to go ahead and type because this method is really hard to explain. They want you to type out the calculations. You will use the log method calculation in that. Okay, so just keep that in mind. You want to do the math calculations and show every step how you got the orders. All right, so you do want to go ahead and type out the rates. Yeah, in the results quiz. Exactly. So make sure you do that in your results quiz. Okay. All right, so let's do another 2 lines. It was lines 3 and 4. Lines 3 and 4. It was, let me go ahead and write it out. Three and 4 is 2, 10 to the minus 3. 2, 10 to the minus 3. This is 1, this is 2, and this is 1.6, 10 to the minus 3, 1.6, 10 to the minus 3. Well, the rate didn't change, so that's going to be kind of easy. So this one's constant, right? This one's constant. And this one's going by times 2, okay? And what's this one? Times 1. That's constant.
It's going to be 0 order, right?
Yes, it's 0 order, very good. Now, how can you get something to be 1? Basically, it's equals to times 2 to the power of 0. You gotta make sure the number here matches that and then just find what order pairs with it to get that number. Okay, so if this was a 3 times, this will be 3 to the power of 0. So this is 0 order, very good. So H plus is 0. I guess I should write 0 so it doesn't look like O. All right, so now that you have the orders, what you do is put them together and you can write a rate law. So we got 3 reactants, rate equals to K, rate constant, times my first reactant is MnO4 negative, and to the power of 2 because I knew it was second order. And then you can write H2C2O4 to the power of 1, first order, and then H plus to the power of 0. Okay, now a lot of times you can write it like that, or it's the same thing as writing this. K MnO4 negative squared H2C2O4. That's literally the same thing. So a lot of times they drop that 1 here and the 0, the power 0. Okay, so now that we have this, we want to go ahead and find K, because the next step in your lab, once you find the rate law like that, you will have to find K for every single mixture. In lecture, we're just going to do it for the first line. And then you just repeat for line 2, 3, and 4 for your lab and get the average K for all of them. Okay, so to find K for line 1, okay? What we're going to do is plug in the rate for line 1. So you take a look on your table up front here on the top. That's the rate for line 1. I'll write that down. And all the concentrations will go in there, okay? So the rate for line 1 is 2.0 times 10 to the minus 4. Oops. When the rate doesn't change despite doubling, tripling the amount of reactant, it's safe to assume the order is 0. Yes. If the rate does not change, even if the reactants change, then it is 0 order. So it's good, like once you practice a lot, you start seeing patterns and it's a lot easier to be able to tell what's 0 first and second. 0 is when the rate doesn't change. First order is when the rate changes with the same number. And second order when the rate changes by the square. Okay? So we got this. We'll write the rate down for number 1. And then equals to K. I'm looking for the K. I don't know what it is, but I can plug in all my concentrations. So MnO4's concentration is 1.0 times 10 to the minus 3 molarity. And I'm going to square this term. And then times H2C2O4, which is 1.0 times 10 to the minus 3 molarity. And that's to the power of 1. I'm not going to worry about that part. I'm just going to do that. Okay? So now I have to solve for K. Take your calculator. I want you guys to do the K for me. Okay? Try this one out because it's got a lot of 10 to the power something something. So I'm going to go ahead and write out how you would do it using algebra. Okay, and then you take these two on the bottom. And you notice these can multiply and just to be to the power of 3 on the bottom right there. So you have to take 2 times 10 to the minus 4 divided by, and then put your brackets in, okay? 1 times 10 to the minus 3, and then cube that number. It's not 200, it's actually bigger than that. Yeah, I think because you have to remember all your stuff. So, and then you gotta remember your units. So I'm gonna go ahead and write down what the bottom number equals to, okay? So can you try to see if we can get that? Write another step for you. So it's very important to know how to like punch numbers in because it starts getting a little complicated, I guess, you know? So 1.0 times 10 to the minus 9. And then it's m to the power of 3. Right, it's a whole bunch of zeros, 10 to the power 5. Yes, very good. So I'm just gonna ahead, right? 2.0, 10 to the power of 5. Then m or m cubed, it's m to the negative 2. And then s to the negative 1 because it's on the bottom. You guys understand this unit way, right? So this is all basically algebra, so gotta kind of get used to it, okay? So that's how you would find the k for step 1. And then if you have, you know, other lines to do, you repeat the same method, plug in the numbers from every line and get the k that way. The key is, if you do not change the temperature, your k should stay the same, ideally. But because there's experimental error, your k will vary a little bit. If your k is all over the place, we know your experimental error is really, really big, okay? So just keep that in mind. All right, I guess we can go ahead and try more problems now. Let's do a few more until you're like, oh yeah, I got so many questions to practice. I want you guys to make sure you're practicing this after class today, okay? Over the weekend as well, so you get really good at it. Here's another one. NH4, ammonium, and 2. Line 1, 2, 3, 4. Some of these are not on your slides. I don't know, I don't remember which is not, which is on. Some of the questions I do from the slide, but a lot of these I pull out from like old test questions. So it's kind of like something you might see on your test kind of deal, okay? So it's definitely a very good idea to practice doing these problems when you're studying your notes. I like to always tell you guys, you know, the same day you learn this, go ahead and try working on the problems again and see if you remember how to do it and can you get the same answers. So we're just gonna start drawing lines, okay? Pick out your lines and you tell me what we wanna do for our lines. One and two for column 1. So 1 and 2 for this first one. Yeah, that works because this is going up by 3. This is constant. This is changing, right? So we can do that. So I'm going to go ahead and do lines. So it says line 1 and 2 for the first one. And then there's another option. We said lines 3 and 4. Let's see if that works. Yeah, that works. Lines 3 and 4. So don't always think it has to be in order, okay? It doesn't. It just so happened that we picked those that are in order. You can go whichever way you want. That works for me. Okay, so let's do the first lines 1 and 2. Lines 1 and 2, it says this one is times 3, agree? This one is constant, or times 1. This one is times what? It looks like it's times 3. If you're not sure, you take this number divided by that. The same way you take this divided by that, okay? What order is NH4? All right, first order. All right, let's do the second one that everyone picked, okay? That one's constant, so it's times 1 or constant. Same thing, okay? This one's times 2. What's happening to your rate? Is it times something? It's times 2. Looks like it, right? Well, that makes it easy. Times 2 means what order is that? You know how I say it's first order for earlier? Because it's 3, and then that 3, and then to the power of 1. And that's how I know it's first order. So this one is times 2 to the power of 1. And it's also first order. So NO2 negative nitrite is first order. Now, if you really know, we're going to write the rate law out. The rate law equals to rate equals K NH4 plus and NO2 negative. This is 2 power 1. You don't really have to write out the 1 if you didn't want to. It's 1 and 1 up there. Okay? So if we wanted to solve for the K for the first line, let's go ahead and do that. I'm just going to do it for the first line. In that, you get to do it for line 1, 2, 3, 4, and do the average of all the Ks. Okay? So rate of 1 is that one, 10.8, 10 to the minus 7. And then times K, and put the first molarity in. And then we'll put the second molarity in. K then equals to 10.8, 10 to the minus 7, divided by these two numbers multiplied together. That's 0.04, 0.04, 0.04. 2.70 times 10 to the minus 4. All right. So here's another question where, yeah, let's do another one where I want to show you where it's a good time to use the log method. Okay, like, I mean, kind of, yeah. We'll try the log method for one of the trials here. So that's that. We found the rate law, and we found the K. I'm gonna write a new question out on the bottom here. Do we have space? I'm gonna go ahead and use another page here. I'm gonna turn the page, okay? Let's try it right here. So it's CHCl3 plus Cl2 goes to CCl4 plus HCl. Sometimes they give you the equation. And then they say, here's my rate law chart on my experiment that I did. You put your reactants in and you do the rate. They did it 4 times. If the K isn't small, it's incorrect. No, that's not true. The K can be big or small, depending on the rate of the reaction. If it's a fast reaction, the rate will be big. Small, then the rate will be really small. I mean, slow reaction rate is small. Okay, so let's go ahead. We have another set here. So start picking your lines for me, okay? So see what lines you guys want to work with. Lines 2 and 3. Yeah, we can do that, lines 2 and 3 for the second one. So one option was lines 2 and 3, so this was right here. And that would go for CL2. Any other suggestions? Lines 1 and 2. Will that work? Let's take a look. 1, 2. Yep, that will work. Lines 1 and 2 from here to here. So then we have our two reactants, okay? So I had, like, you know, we try to pick the ones that are only one changing. So I have some students who really don't know which lines to pick, and sometimes to pick line 3 and 4. Why would you pick, well, you could do it like with line 3 and 4, but like both of them are changing. It's so confusing. So that's not a good option. Okay, so let's take to line 1 and 2, line 3, 2 and 3 for now. If you see any other combinations, let me know, okay? So let's go ahead and take a look at the first two lines. I guess we'll do lines 1 and 2 for now, the purple one. This is times 2 times constant. What's this one? This is about times 2, right? Because it's 3, 5, and 70, so. Agree? So if it's 2, and that's 2 to the power of what? 1. Yes, that's right. The rate isn't a pretty number, so we use the log method. Very good. For lines 2 and 3, okay, when we get to that, I'll show you why you would do the log method, because it's not easily predictable that way, just by looking. Yeah, but a lot of times in lecture, our problems are really easy to tell, so you don't really have to do the log method every time. But you know, in this case, it will become useful. Let's focus on these two first. I guess I'll go ahead and write down, based on this, 2 and constant 2 to the power 1, I'll go ahead and write down CL3 is first order. Now let's take a look at the second lines that we chose to use. This one's constant, so no change. This one's times 2, and what's this one? You're like, okay, so take 0.0098 divided by 0.0069. And it's like 1.42 or something like that. So, and you're like, okay, there's no way it's not to the power 0, it's not to the power 1, it's not to the power 2. You see that? And so like, okay, so I don't know what the number will be. When you get something like this is when the log method becomes really useful. Okay, so let's go ahead and do the log method. So we're gonna do rate for 3 divided by rate for 2. Okay, so for lines 2 and 3, my rate for 3 is, I guess I'll write the formula out first so you know where I was getting my numbers from. And we actually know CHCl3 is first order. You can actually either plug in 1 here or you plug in n, but you know, well, I'll put n here and I'll write n equals to 1. Because it depends if you already solved for that one before that or not. The second one is, oh, I'm not writing numbers yet. Hold on. Erase. Cl2m. Okay. And then rate 2, same thing. Okay, and then you put the items in there. So we already know from the top here that n equals to 1. We already know that, okay? And then I want to divide rates 2 and 3, so go ahead and write the rates out. So this is 0.0069 equals to k 0.020. And I already know that's 1. I'm going to go ahead and fill in 1. CHCl2. Ooh, 3 is 98. Two. So we can see that ends up being the 1.42 thing that we were talking about, right? So let's put that there. And then the K crosses off, so we don't have to worry about it. That crosses off. That becomes 1. So now you have 0.00, 0.020, 0.010. So that's 2, or it's 2 to the power m. You guys agree? Right? So when you see something like that, you can literally write down the formula up here on your own, really. You didn't have to go through the motion. But for our lab purposes, it's always, you have to show where the numbers came from. So you have to write out the steps. Okay? But if you're doing your own work at home and you're doing for like a quiz or a test or something, they didn't ask you to show you all your work. You can just do this. You can go straight to this. Once you see this, you're like 2 to the power of what equals to 1.42. You just set it up like that. Okay, so once you get that, we use the log method. We log both ways, log 1.42, and then log 2 to the power of m, where the m comes to the front. Okay, so now this turns into this. I'm trying to write out more of the steps, but if you are comfortable with your log and calculations, you really don't have to write out so many steps, okay? So m equals to log 1.42 over log of 2. What do you guys get then? So try on your calculations, in your calculator, okay? So you get point, it's not in seconds because this is an order, it's only just gonna be a number, okay? First order, second order. So we're getting 5.505, 506, something like that, okay. So that will tell us this is half order, okay? So m here, we'll just round it to half. So remember I said whole numbers or halves. This is a half order, all right? So when you write your rate law, it will be rate equals to K CHCl3, that's to the power of 1, and then this one Cl2, that's to the power of half. All right, so hopefully that makes sense. So when do you use the log method? When does it become really helpful? When your numbers are not pretty like that. And if you get comfortable enough, you don't really have to set all this up. You can just say 2 to the power of what becomes 1.42. And then you set it up to solve for that, okay? So that's how you can really save time, you know, when you have to write, you don't have to write so many items here. But for our lab purposes, you do have to show your work.